Hello. Okay. So in this lecture, I'm going to discuss about the architecture of 8086. So what I have observed that most of the students are getting trouble to understand the architecture of 8086. So let me tell you, if you want to understand the architecture of 8086, you need to understand two things. One is memory segmentation of 8086, how the memory is segmented in different segments, and how the instruction is executed in 8086. These two things, if you understand, then you can easily understand the architecture of 8086. Okay. So before directly going through the architecture of 8086, first I'll discuss how the instruction is executed in 8086. Now, uh, if you can remember from my previous lecture, uh, in 8085, how the instruction is executed. Then we'll come to 8086. Now in 8085, how the instruction is executed actually, for each of the instruction, three steps will be there. To execute any instruction, three operations are performed one by one. First operation is known as fetch, FETCH fetch, then decode, then execute. So these three steps have to be performed for each of the instruction. Okay, in 8085. So suppose if you are means if your 8085 processor executing instruction number I1, then first it need to do fetch for I1, then it needs to do decode of I1, then it has to do the execution of I1. Okay, these three steps to be followed. Then only it can do the execution of I2. So for I2 also fetch, decode, execute. Then if you complete these three operations, then you can go for the next instruction I3. Then here also fetch, decode, execute you need to perform. However, in case of 8086, things are different. In case of 8086, the pipelining is applicable. What is pipelining? Here in 8086, how the instruction is executed. Suppose for instruction I1, fetch is completed, decoding is completed, and it is now in execution step. Okay, it comes to execution step. Meanwhile, you can do the fetching of instruction I2, instruction I3, instruction I4, or so on. Okay. So when instruction I1 execution is going on at the time or simultaneously I2, then I3, then I4 instruction fetching operation can be performed. Okay. So it means that it is not required the completion of all the three steps for each of the instruction. When the third step is going on for the first instruction, then the fetching operation can be performed for the subsequent instruction. Okay. And this is the concept of pipelining. Okay. Now this is followed in 8086. So if you have understood this concept, then it is very easy to understand the architecture of 8086. Other than that, in 8086, you have memory unit, some memory will be there, and there comes the concept of memory segmentation. The memory is divided into four segments. So whatever external memory you are having or memory you are having in 8086, it is having these four things. Okay, four segments will be there in the memory. The segments are code segment. Okay, CS means code segment. This is known as code segment. So let me write down the full form. Code segment. Then the second one is SS. Uh, that is stack segment. SS stands for stack. STACK stack segment. Then you have data segment, DS. Then you have extra segment, ES, extra segment. So these are the four segments of memory. Okay, so this is the way memory segmentation is done. Now, in order to calculate a an address, okay, you need to follow this rule in case of 8086. Okay, the rule is physical address. Now, before coming to physical address, few things I will tell. Though in my previous lecture I discussed about these points, but still briefly I will tell few things. So if you consider any memory, two things you need to think of. One is address, the other one is data. Okay. If you consider a memory, you need to take care of, or you need to understand two things. One is address, the other one is data. So what is address? Address means in case of 8086, as the size of address bus is 20 bit in binary. So in hexadecimal, if you convert, if you have 20 bits in binary, in hexadecimal it will be 5 digits. Okay. So 5 digits address will be there. And in this 5-digit address means it will have 5-digit combination of address. Okay. And in each of the address or each of the location, 8-bit data will be there, 8-bit in binary, 8-bit in binary. So it means that in hexadecimal, it will be 2 bits, and 8-bit in binary, that is nothing but 1 byte. This I have discussed in my previous lecture also. So what I'm saying, each of the memory location can have 1 byte of data, and if each memory location is given by 5 digit. So you have address, you have data. Okay. Now, so how the address is calculated? Okay. So suppose another example I'll give. Suppose I'm trying to send one parcel in your home. So what I need to give? I need to have your address. So this is the address, and in the home you will be there maybe. Okay. So you can consider as a data. So this is some sort of similar thing. What I try to make a correlation between these two things. Okay. So it will have some address and it will have some data. So how the physical address is calculated in 8086? Physical address is calculated, PA. Physical address is calculated as starting address of segment register. Okay, so for each of the segment, some segment register will be there. For each of the segment, some segment register is there, which will have the starting address of each of the segment. Okay, so starting address of the segment register has to be multiplied, or starting address of the segment. Actually, I need to write starting address of segment. It has to be multiplied 10, and it's hexadecimal value actually. Plus you need to add offset. This is the way the physical address is calculated. Now, where I'll get the code segment means which register will contain the starting address of code segment. This is known as CSR, code segment register. Code segment register will contain the starting address of code segment. Okay, this will contain the starting address of code segment. Then for stack segment, okay, let me write here itself. Okay, so what I said till now, let me use some different color. Yeah, so CSR, code segment register, will have the starting address of code segment. Then stack segment register will have the starting address of stack segment. Data segment register will have the starting address of data segment. Then extra segment register will have the starting address of extra segment. Okay, so for each of the segment, some segment register will be there in 8086, which will contain the starting address of that segment. So for code segment in 8086, some register is there that is known as code segment register. For stack segment, it is known as stack segment register, SSR it should be. For data segment, it is DSR, data segment register. For extra segment is extra segment register. So these are the registers given to have the starting address for each of the segment. And other than that, some registers will be there which will be used to get the offset value. What is offset value? Suppose what I'm trying to say, for each of the segment, what I told, some register will be there which will contain the starting address. But inside each of the segment, some individual locations are there. Each of the segments, some individual locations are there. So how many locations are there? So that location can be from 0000, and all this I am representing in hexadecimal only, sorry, H, to FFFF. So this address means that offset value can vary from 000 to FFFFH. Okay, understood? So now I'll write what are the offset registers are given for this segment. So one Offset register will be there, one or multiple also can be there for each of the segment, which will give you the offset value. Now, which are this registered? So for code segment, the offset register is IP or instruction pointer. This register will have the offset value for this code segment. Now for stack segment, it can be stack SP stack pointer or it can be BP base pointer. These two can be there. So these two registers can have the offset value of stack segment, maybe stack pointer or it can be base pointer. Then come for the data segment, it will be SI or source index. The full form of SI is source index. Now for ES, it will be DI. DI is known as destination index. Okay, so for data segment, it will be SI of SI means SI is carrying the offset. Then for extra segment, DI is carrying the offset. Okay, so DI stands for destination index. SI stands for source index. SP is the stack pointer, BP is the base pointer, IP is the instruction pointer. Okay, so these are the registers which will contain the offset value for this particular segment. Okay, so this is the formula you need to follow. Now you can easily calculate the physical address. So physical address, suppose if you consider code segment, how it will be calculated? Your code segment register will have the starting address. It has to be multiplied with 10 and it has to be added with the content of instruction pointer, because for code segment instruction pointer will give you the offset. And addition of these two things will give you the physical address of that particular location, what you want to access in the code segment. So same thing is applicable for all the remaining segments. Okay, so if you have understood these two things, means one is instruction execution in 8086 and this memory segmentation of 8086 and how this physical address is calculated. If you have understood these things, you can easily understand the architecture of 8086. Now I'll go directly to the architecture of 8086. Okay, now the architecture of 8086 contains two parts. One is known as BIU or bus interface unit. BIU stands for bus interface unit. And the other unit is known as execution unit. That is EU. EU is execution unit. So two units are there in the architecture of 8086, bus interface unit and execution unit. Now let me tell you what is the purpose of bus interface unit. So now how the instruction is executed. You know, three steps to be followed. One is fetch, then execute. Okay, so bus interface unit purpose is to fetch the instruction. Okay, what is the purpose of BIU? BIU purpose is it will fetch the instruction. What is the purpose of EU? EU is used to execute the instruction. Now, what is the purpose of, means who will do the decode operation? In the execution unit, some control unit you can see here, this control unit will do the execution of these things. Okay, that is also included in the execution unit part. Okay, so the purpose of bus interface unit is to fetch the instruction and then decode and execution will be done in this execution unit. Okay, fine. Now, as I told earlier in my previous videos also I told, suppose if you are writing some program for 8086, generally you will write in assembly language program. Okay, then some assembler will be there which will convert the assembly language code to machine language code, and that code will be stored in the code segment of this segment register. You know, I discussed about the code segment. So those instruction will be stored in the coded form in this code segment. Now, if processor wants to execute each of the instruction, how it will do? First of all, it needs to find out from where the instruction has to be fetched. So for each of the instruction, first of all, processor has to fetch the instruction. Okay. So fetching will be done the bus interface unit. Now, in order to fetch the instruction, first of all, processor has to calculate the physical address from where the instruction has to be fetched. Suppose if we talk about code segment, suppose one instruction is present in the code segment. So first of all, processor will try to find out the physical address of that particular instruction. Okay, now how to calculate the physical address? I already explained. So processor will first calculate the physical address. Now suppose if the instruction is present in the code segment, how the calculation will be done? Starting address of that code segment, and you know in the 8086 some register will be there, that is known as code segment register. The content of code segment register will be multiplied with 10, and that has to be added with the offset value. And you know for code segment, which register is having the offset value, that is instruction pointer will have the offset value. So you see what BIU is doing. So you see in BIU some arithmetic operator is there that will do the this calculation of the physical address. So physical address is calculated by segment register content, and it is multiplied with 10, and it is added with the offset. So that operation is done by this arithmetic unit, and that is present in the BIU. Okay, so see in the BIU, what are the registers are present? CS. Is it code segment? Not. This is the code segment register, because code segment is present in the memory unit. Okay, as I am talking about the architecture, this CS represent code segment register. Okay, now where the code segment is present, I already told this is present in the memory, because memory is divided into 4 segment: code segment, stack segment, data segment, extra segment. Memory is present in different means memory is a different unit. Okay, that has to be means added, or that has to be connected with the 8086. Okay, so if processor wants to fetch any instruction, it has to first calculate the physical address of that corresponding location from where it needs to fetch the instruction. So that calculation will be done by this arithmetic unit. And how the calculation is done, as I already told, physical address equal to segment register content, it has to be multiplied by 10, and it has to be added with offset. So if I consider code segment of the memory unit, suppose my instruction is present in the code segment of the memory unit. So what processor will do? It will calculate its physical address, the instruction which it needs to execute or which it needs to be fetched. That address will be calculated by this particular formula. Okay, now who will give this segment register value, starting address value? So if it is code segment, this will give the means this will give the content, means this will give the address value, means CSR value will be given by this one. So this CS represent the code segment register, SS represent the stack segment register, DS represent the data segment register, ES represent the extra segment register. So these all are the registers, and the corresponding segment is present in the memory unit. So that segment can be code segment, can be stack segment, can be data segment, can be extra segment. So these things are present in the memory, and their corresponding register is present in the inside the processor. So, okay, so CS is the register, the CSR is the register, stack segment register, data segment register, extra segment register. And I told for code segment, what is the offset value, which register will contain the offset value, that is IP. So IP is also present here, instruction pointer is also present here. So using this thing, it will calculate the physical address from where it needs to fetch the instruction. So that instruction will come through the data bus, because you have calculated the physical address, and that address will be given through address bus, and what address you have pointed out, from there the instruction will be carried out through the data bus. Okay, so bus interface unit will fetch the instruction. Fetch means it will collect the instruction from the code segment to this processor. Okay, after fetching, what it will do, it will put in this 6-byte instruction queue. So the size of this prefetch queue is nothing but 6 bytes. The size of this prefetch queue is 6 bytes. Okay, so as I told in the beginning, if you can remember, when the execution of one instruction is going on at that time, it can fetch multiple instruction according to their size. So how many instruction it can fetch, that is not means that is not the main thing. How many bytes? Okay, how many bytes of instruction it can fetch, that is 6 bytes. Okay, means if suppose Try to understand what I'm saying. Suppose execution of I1 is going on. At that time, how many instruction it can store, or it can queue in this prefetch queue, that is depending on the size of the instruction. How many bytes of instructions are there? Suppose I2 is having 2 bytes. I3 is having 2 bytes. I4 is having 2 bytes. So 2, 2, 2. So how much it is? 2 to 2 means 6 bytes. So my queue is full now. So in the 6 byte, how many instructions are present? For this particular example, 1, 2, 3 instructions are present. So for this particular example, 3 instruction can be here in this prefetch queue, because instruction means here its corresponding binary representation is given. Okay, I already told, when we are writing the assembly language program, some assembler will be there which will convert the assembly language program to machine language code, and machine language code is nothing but the combination of 1 and 0. So for each of the instruction, this is nothing but the combination of 1 and 0, and that will, after doing the fetching by using bus interface unit, those instruction will be stored in the prefetch queue. Okay, so how many bytes you can store here? Maximum 6 bytes. So if your instruction, each of the instruction are of 2 byte, you can store 3 instructions here, because as each of the instruction is of 2 byte, then 3 instruction will be having 6 byte. Suppose your instruction are of 3 bytes, then 3 into 2, 6 bytes means 2 instruction you can store. If your instruction is of 6 byte, then only 1 instruction you can store here. Okay, so this prefetch queue is not telling about how many instruction you can store. It is giving the information how many bytes of instruction you can store, how many bytes you can store in the prefetch queue. Okay, so if your instruction is 6 byte, you can store 1 instruction. If your instruction, each of the instruction are of 2 byte, you can store 3 instructions. Each of the instruction is of 3 byte, then you can store 2 instruction in the prefetch. Okay, and if you know, in 8086 instruction can be of 1 byte, it can be of 2 byte, it can be of 3 byte, 4 byte, 5 byte, and it can be up to 6 byte. So the maximum size of the instruction in 8086 can be of 6 byte. So that's why the size of the prefetch queue is 6 byte, so that it can store one complete instruction of 6 byte. Okay, which is the largest instruction in case of 8086. Now, so what I said, first of all, processor has to fetch the instruction from the memory. So processor means bus interface unit, suppose taken the fetch means it has taken the instruction from the memory unit to the 8086 processor. How? First of all, it calculates the physical address of the segment from where it needs to collect the instruction. So for that, this summary unit is given, or this arithmetic unit is given, which is calculating the physical address. Then it has fetched that instruction through the data bus. And after that, it will put in the prefetch queue. And in the prefetch queue, how many bytes of instruction you can put? That is maximum you can put 6 bytes here. And how many instruction you can put, that is depending on what is the size of the instruction. Is it of 2 byte, 3 byte, 1 byte, or 6 byte? Okay. Now after that, what it will be done? This instruction will come to the control unit. Okay. Now what is the purpose of control unit? Till now, I discussed about the fetching of the instruction. After fetching, what you need to do? All of you know, you need to do decode. Because I already told, when you are writing the program, you are writing in assembly language, but in the processor, thus means in the memory unit, the program or instruction will be stored in the form of binary digits. So when this particular combination of 1010 will come in the control unit, this control unit will try to decode the instruction. Means this is a particular combination of 1010. Yeah, this is talking about addition, or it is talking about subtraction, or it is talking about the move operation. So the control unit is used to do the decoding of the combination of 1010. Means when this 1010 combination will come, it will try to find out which operation it is talking about. Okay, so whether it is addition operation, subtraction operation, or any move operation need to be done, or maybe some other operation need to be done, that particular instruction decoding will be done. Okay, in the control unit. After that, what need to be done? As decoding is done, then the last step is execution. So execution will be performed in this section. Now for that, you have four general purpose register. These are known as AX, BX, CX, DX. AX stands for accumulator register AX, BX is for base register, BX stands for base register, C is the count, and DX is the data. Okay, so all these details are given here. AX is the accumulator, BX is the base, CX is the count, and DX is the data. Now AX is further divided into two parts. AH and AL. BX is divided into two parts, BH and BL, means higher part, lower part, and each of the part is having 8 bit. Okay, so in combination AX is 16 bit. Okay, now if you can remember in my previous lecture when I was discussing the features of 8086, I told 8086 has 14 registers and each of the register of 16 bits. Okay, so till now, whatever the registers I have discussed, okay, for 8086, suppose this code segment register, data segment register, stack segment register, extra segment, or instruction pointer, all these registers are 16 bit only. Okay, so that is applicable here also. AX register means accumulator is also 16 bit, base register 16 bit, count register, data register, stack pointer, base pointer, source index, destination index, all these registers are 16 bit registers in case of 8086. Okay, now out of this register, these four are known as general purpose registers. General purpose. Because when you are doing some addition operation, subtraction, multiplication, so these registers will be used. Okay, this AX, BX, CX, DX. That's why these registers are known as general purpose register. Means programmer can access or save their values to do some certain operation. Suppose if you want to add 6, 5 or 5 with 6, then first of all you need to give 5 to one of the register, 6 to other register. Then through the register you can add the value of 5 and 6. So for that we have given the register of AX, BX, CX, DX. So using this register, you can do the operation. Okay, so that's why these registers are known as general purpose register. You can use for your purpose. Okay, programmer use can use their purpose. Then stack pointer and base pointer, these are known as pointer register, and these are index, source index and destination index. Okay, so what is the purpose of source index? If you can remember, I already told this will be used as a offset register for data segment. DI used for the offset register for extra segment. Then BP is also used for the BP is used for the offset register for stack segment. So all these things I already told BP, and SP will contain the top of the stack. So in 8086 stack operation will be there. So if you do the push operation, so things will be added on the top of the stack. And if you use the pop instruction, so things will be removed from the top of the stack. So at that time, if the stack is getting updated, or if the pointer of the stack is getting updated, or if it is getting means increase or decrease, that value will be carried by the stack pointer. So that position will be carried by the stack pointer. Okay, so I think this registers idea is clear for what purpose these registers are used. Okay, now come to this architecture from where we have started. So when this decoding operation was done for a particular instruction, then execution operation will be done, and you will be doing this execution operation. So for that you have this register. Suppose your instruction is given to do the addition operation. So one of the number will be stored in AX, other number will be stored in BX, and the addition will be performed between these two, and that will be done through this unit ALU, arithmetic logic unit. So what is the purpose of ALU? It will do the arithmetic or logical operation. Suppose if it is asked to add two numbers, what it will do? One of the numbers, suppose one of the number you are saving in AX, other number you have stored in BX. So one number will come here, other number will come here. Addition operation will be done. And after addition, what result you have got, that will be stored in some other register. This is a very well-known instruction for 8086, add AX, BX. So what is the purpose of this instruction? It will add the content of AX with the content of BX, and what result will be there means addition of AX and BX, what result you have got, that will be again stored in AX. That is a well-known instruction of 8086. Okay. So when you are getting the result, that result will be again be stored in some register. Okay. For example, if you do that, if you use this instruction add AX comma BX, so the content of AX will be added to the content of BX, and the result, whatever you have obtained, that will be again stored in AX. So that's why this line is given, means result is again stored in this register. Okay. So I think now the purpose of ALU is clear. Yeah. Then the next thing is operand. This is some sort of register which is used by the processor for its temporary storage of data. Okay, so if processor does some operation where the temporary storage of values is required, that operand register will be used by the processor, and this you cannot use. Programmer cannot use this register. So this is a very well known operation. Suppose if you are doing the exchange of two data, means if your processor actually doing the exchange of the data between AX and BX, suppose. So what you have to do? The content of BX, if you directly give to AX, means AX content will be means removed. So what processor does? The content of AX, it will be stored in some operand register, this register, and it will collect the content of BX to AX, and after that, this this temporary register content will be given to BX register, so that exchange operation can be performed. So this is one of the example. For many other examples also this operand register is used, and flag. So I'll make some separate video for the flag register. So what is the purpose of flag register in a brief sense? If you want to tell, then the purpose of flag register is nothing but, suppose if you do some arithmetic logic operation or any operation, if you do, the status of the operation will be reflected in the flag register. Okay, whether any carry came in the operation, or whether the result is 0 or not, and what is the status of the sign flag, what is the status of the carry flag, or whether the result is 0. Yeah, already I told. And auxiliary carry is there or not, overflow occurred or not, all this information will be given or reflected in the flag register. So I'll make a separate video on the flag register. Okay, so this is the main two units of the 8086 architecture, and this is the way the instruction execution is done in 8086 processor. So in a briefly, if I want to tell, what is the process I told? First of all, instruction will be fetched by the bus interface unit. So for that, the physical location of that instruction will be calculated by this summing unit, and that is calculated by the segment register starting address, means where the instruction is present, which one you want to execute, or where, what processor wants to execute, what is the where the instruction is present. So you know 4 segments are there. In which segment this instruction is present? Generally, you know instruction is present in the code segment only. So that code segment address means starting address, you will get the code segment register here, and it will be multiplied by 10, and it will be added to the offset. And you know for the code segment, the offset register is IP. The content of IP will be added to get the physical address. So when the physical address will be calculated, that particular instruction will be taken through data bus by in this bus interface unit, and after that it will store this thing in the prefetch queue. And how many bytes it can store in the prefetch queue? 6 bytes. Okay, and after that, the control unit will do the decoding of this instruction, and this instruction, when it is getting decoded, it will be given to the execution unit, and in the execution unit, some general purpose registers are there where programmer can access this instruction, means use this register for their operation, and some pointers are there which are used for the offset address, which are used for the offset address for different segments. And ALU will perform the arithmetic and logical operation. And you know what is arithmetic operation and what is logical operation. Suppose addition, multiplication, subtraction, division, these are arithmetic operation. Logical operation and or XOR, these are uh, uh, logical operation. And then operand registers. Operand register is there, which is used for the internal temporary storage of data by the processor, and some flag register is there, which is used for the this thing for the, means suppose some operation is performed. So whatever the result you got, its status will be shown by this flag register. Okay. And execution unit in general, it does the execution of the instruction. Now, let me tell you one important thing. Though we have completed the entire architecture, one thing I need to tell you. Here you see from the prefetch queue, two lines are given. One line is directly coming to the control unit, and other thing is coming to the execution unit. Why these two lines are given? Because some instruction directly have some opcode. Suppose if you consider this instruction, move ax comma bx. This instruction is having some direct opcode. Okay, so directly some 1010, some combination of 1 and 0 will be there for this but entire instruction. Okay, so control unit will try to decode this instruction, and after that this decoded form means whatever decoded after decoding what operation it has identified, based on that operation control signal will be generated in the control unit, and some operation will be performed. Okay, but if you consider this instruction, suppose move ax comma 111h. In this case, for move ax, some opcode will be there, and 111h is some operand part. So no need to find any opcode for 1111. So that 1111 will directly come through this line to the execution unit, whereas for move ax, some opcode will be there that will be decoded by the control unit decoder. Okay, so that's why these two separate lines are given. So hopefully now the architecture of 8086 is clear to everyone. Thank you very much.